In mathematics, mathematical physics and the theory of stochastic processes, a harmonic function is a twice continuously differentiable function f u r which satisfies Laplace's equation, i.e., everywhere on U. This is usually written as or examples. Examples of harmonic functions of two variables are the real or imaginary part of any holomorphic function. The function, this is a special case of the example above, as, and is a holomorphic function. The function, defined on examples of harmonic functions are three variables are given in the table below with. Harmonic functions that arise in physics are determined by their singularities and boundary conditions. On regions without boundaries, adding the real or imaginary part of any entire function will produce a harmonic function with the same singularity. So in this case the harmonic function is not determined by its singularities. However, we can make the solution unique in physical situations by requiring that the solution goes to zero as you go to infinity. In this case, uniqueness follows by Liouville's theorem. The singular points of the harmonic functions above are expressed as charges and charge densities using the terminology of electrostatics. And so the corresponding harmonic function will be proportional to the electrostatic potential due to these charge distributions. Each function above will yield another harmonic function when multiplied by a constant, rotated, and/or has a constant added. The inversion of each function will yield another harmonic function which has singularities which are the images of the original singularities in a spherical mirror. Also, the sum of any two harmonic functions will yield another harmonic function. Finally, examples of harmonic functions of n variables are the constant, linear and affine functions on all of Rn, the function on for n greater than 2. Remarks. The set of harmonic functions on a given open set U can be seen as the kernel of the Laplace operator delta and is therefore a vector space over R. Sums, differences and scalar multiples of harmonic functions are again harmonic. If f is a harmonic function on U, then all partial derivatives of f are also harmonic functions on U. The Laplace operator delta and the partial derivative operator will commute on this class of functions. In several ways, the harmonic functions are real analogues to holomorphic functions. All harmonic functions are analytic, i.e., they can be locally expressed as power series. This is a general fact about elliptic operators, of which the Laplacian is a major example. The uniform limit of a convergent sequence of harmonic functions is still harmonic. This is true because every continuous function satisfying the mean value property is harmonic. Consider the sequence on times r defined by. This sequence is harmonic and converges uniformly to the zero function. However, note that the partial derivatives are not uniformly convergent to the zero function. This example shows the importance of relying on the mean value property and continuity to argue that the limit is harmonic. Connections with complex function theory. The real and imaginary part of any holomorphic function yield harmonic functions on R2. Conversely, any harmonic function U on an open subset omega of R2 is locally the real part of a holomorphic function. This is immediately seen observing that, writing z equals x plus iy, the complex function g equals ux minus iuy is holomorphic in omega because it satisfies the Cauchy-Riemann equations. Therefore, G has locally a primitive f, and U is the real part of f up to a constant, as Ux is the real part of. Although the above correspondence with holomorphic functions only holds for functions of two real variables, harmonic functions in n variables still enjoy a number of properties typical of holomorphic functions. They are analytic, they have a maximum principle and a mean value principle. A theorem of removal of singularities as well as a Liouville theorem holds for them in analogy to the corresponding theorems in complex functions theory. Properties of harmonic functions. Some important properties of harmonic functions can be deduced from Laplace's equation. Regularity theorem for harmonic functions. Harmonic functions are infinitely differentiable. In fact, harmonic functions are real analytic. Maximum principal harmonic functions satisfy the following maximum principle. If K is any compact subset of U, then f, restricted to K, attains its maximum and minimum on the boundary of K. If U is connected, this means that f cannot have local maxima or minima, other than the exceptional case where f is constant. Similar properties can be shown for subharmonic functions. The mean value property: if B is a ball with center x and radius r which is completely contained in the open set omega Rn, then the value u of the harmonic function u, omega r at the center of the ball is given by the average value of u on the surface of the ball. This average value is also equal to the average value of u in the interior of the ball. In other words, where omega n is the area of the unit sphere in n dimensions and sigma is the n one-dimensional surface measure. Conversely, all locally integrable functions satisfying the mean value property are both infinitely differentiable and harmonic. In terms of convolutions, if denotes the characteristic function of the ball with radius r about the origin, normalized so that the function u is harmonic on omega if and only if as soon as b omega. Sketch of the proof. The proof of the mean value property of the harmonic functions and its converse follows immediately, observing that the non-homogeneous equation for any 0 less than s less than r admits an easy explicit solution Wr s of class E1, one with compact support in B. Thus, if U is harmonic in omega holds in the set omega r of all points x in width. Since U is continuous in omega, U asterisk chi r converges to U as S0, showing the mean value property for U in omega. Conversely, if U is any function satisfying the mean value property in omega, that is, holds in omega r for all 0 less than s less than r, then, iterating m times the convolution with chi r1 has, so that U is because the m-fold iterated convolution of chi r is of class with support B. Since r and m are arbitrary, U is 2. Moreover, for all 0 less than s less than r, so that delta U equals 0 in omega by the fundamental theorem of the calculus of variations, proving the equivalence between harmonicity and mean value property. This statement of the mean value property can be generalized as follows. If h is any spherically symmetric function supported in B such that h equals 1, then u equals h asterisk u. In other words, we can take the weighted average of u about a point and recover u. In particular, by taking h to be a C-infinity function, we can recover the value of u at any point even if we only know how u acts as a distribution. See Weyls' lemma. Harnack's inequality: let U be a non-negative harmonic function in a bounded domain omega. Then for every connected set Harnack's inequality holds for some constant C that depends only on V and omega. Removal of singularities: the following principle of removal of singularities holds for harmonic functions. If f is a harmonic function defined on a dotted open subset of Rn, which is less singular at x0 than the fundamental solution, that is, then f extends to a harmonic function on omega. Leopold's theorem: if f is a harmonic function defined on all of Rn which is bounded above or bounded below, then f is constant. Edward Nelson gave a particularly short proof of this theorem, using the mean value property mentioned above. Given 2 points, choose 2 balls with the given points as centers and of equal radius. If the radius is large enough, the 2 balls will coincide except for an arbitrarily small proportion of their volume. Since f is bounded, the averages of it over the 2 balls are arbitrarily close, and so f assumes the same value at any 2 points. Generalizations. Weakly harmonic function: a function is weakly harmonic if it satisfies Laplace's equation in a weak sense. A weakly harmonic function coincides almost everywhere with a strongly harmonic function, and is in particular smooth. A weakly harmonic distribution is precisely the distribution associated to a strongly harmonic function, and so also is smooth. This is Weyl's lemma. There are other weak formulations of Laplace's equation that are often useful, one of which is Dirichlet's principle, representing harmonic functions in the Sobolev space H1 as the minimizers of the Dirichlet energy integral with respect to local variations, that is, all functions such that Jj holds for all or equivalently. For all harmonic functions on manifolds, harmonic functions can be defined on an arbitrary Riemannian manifold, using the Laplace Beltrami operator delta. In this context, a function is called harmonic if many of the properties of harmonic functions on domains in Euclidean space carry over to this more general setting, including the mean value theorem, the maximum principle, and the Harmonic inequality. With the exception of the mean value theorem, these are easy consequences of the corresponding results for general linear elliptic partial differential equations of the second order. Subharmonic functions. A C2 function that satisfies delta f0 is called subharmonic. This condition guarantees that the maximum principle will hold, although other properties of harmonic functions may fail. More generally, a function is subharmonic if and only if, in the interior of any ball in its domain, its graph lies below that of the harmonic function interpolating its boundary values on the ball. Harmonic forms. One generalization of the study of harmonic functions is the study of harmonic forms on Riemannian manifolds, and it is related to the study of cohomology. Also, it is possible to define harmonic vector-valued functions, or harmonic maps of two Riemannian manifolds, which are critical points of a generalized Dirichlet energy functional. This kind of harmonic maps appear in the theory of minimal surfaces. For example, a curve, that is, a map from an interval in R to a Riemannian manifold, is a harmonic map if and only if it is a geodesic. Harmonic maps between manifolds. If M and N are two Riemannian manifolds, then a harmonic map U Mn is defined to be a critical point of the Dirichlet energy in which do. Trademark Tn is the differential of U, and the norm is that induced by the metric on M and that on N on the tensor product bundle T** mu-1 tera-Newton. Important special cases of harmonic maps between manifolds include minimal surfaces, which are precisely the harmonic immersions of a surface into three-dimensional Euclidean space. More generally, minimal submanifolds are harmonic immersions of one manifold in another. Harmonic coordinates are a harmonic diffeomorphism from a manifold to an open subset of a Euclidean space of the same dimension.